The idea is called visible light communication. Now, light's already used to carry data through optical fibres, and we even routinely zap data across our rooms using infrared light whenever we click the TV remote. The idea of visible light communication is that you're piggybacking data on the very same light that you use to brighten a room up. Now, it could offer vital extra data capacity, streaming high-definition movies and things like that, straining Wi-Fi networks, and there's not much space left for extra transmission channels in the radio and microwave spectrum. So if you're going to do it with light, you need a nice quality white light, and you need it to switch on and off very quickly, far too fast to the eye to see, so that it can transmit the data.
So the idea then is you have some kind of light source and you superimpose on the light coming out of that light source a pattern of basically the light turning on and off as pulses, which some detector on your machine can register and decode that code of flashes of light. I suppose it's like megahertz Morse code, isn't it? And that's the data.
Exactly. If you think about the signal lamps that the Navy actually still use, I think, in some conditions, where you have just a big light with shutters on it mounted on the side of a ship, and they use the shutters to switch that light on and off. They're sending messages that way. It's the same idea. There are actually lots of different ways that you could encode the data. This flashing idea is probably the simplest, but it gives you the general idea of how they're planning to do it.
But in this day and age of trying to be as economically efficient with our energy use as possible, this is encouraging people to leave the lights on.
I think the point is that while you're working in an office, you're very likely to have the lights on. And this wouldn't necessarily be the only data route that you use. It would supplement existing networks.
Now, I heard this story first being touted. It must be more than a decade ago that people were saying they were going to try and use light in this way. So something must have now changed to make it more of a reality. So what's been the step forward?
If you want very fast switching light, really you need light emitting diodes, LEDs. And if you're using an LED to produce a nice natural white light, you start with a blue LED and then you coat it with materials called phosphors. These absorb some of the blue light and then re-emit the energy as green or red light. So you get a sort of softer, more natural spectrum of light. They take the edge off this harsh blue. The trouble is all the conventional phosphors that are used for this, they take microseconds to fade away once they've been illuminated by a pulse of blue light. So they're not much good for the sort of fast on and off switching you'd need for decent data transmission. For that, you'd need them to switch on and off billions of times a second so that you can send gigabits of data per second. Now, a team of scientists at the University of St Andrews have developed a solution. Rather than using inorganic phosphors, they've used two organic semiconducting polymers. These are long carbon-based molecules, and they can switch on and off much more quickly, and they emit a broader spectrum of light that helps to improve the quality. One of these polymers absorbs some of the blue light and re-emits it as green, and the second one then steals some energy from the first polymer and emits that as orange-red light. Together they produce a light which is a lot higher quality than previous efforts. It's pretty close to what you'd expect in an office environment. Crucially, they can switch on and off in less than 1 nanosecond. So that means they were able to send data at 350 megabits per second without much error at all. That's 35 times faster than any commercially available phosphor could achieve.